In section 11.2, we'll build on what we've learned about polar bonds to discover polar molecules. Specifically, we'll revisit the idea of the dipole moment and describe how it applies to molecules. Let's begin. Differences in electronegativity between atoms can lead to an unequal sharing of electrons. The polar bond that results will have a dipole, or partial positive charge on the less electronegative element, and a partial negative charge on the more electronegative element. If we consider the effect of polar bonds and the molecular geometry of a molecule, we can predict the molecular polarity. To do this, we need to consider the individual dipoles of each bond to see if they will sum in one direction or cancel each other out. If they do sum in one direction, we can indicate the molecular dipole using the same partial positive and partial negative notations, which will be very important when you study intermolecular forces next semester. Recall that electronegativity increases from left to right across a period and up a column. Fluorine, our most electronegative element, is assigned an electronegativity of 4.0. Oxygen, nitrogen, and chlorine are also very electronegative, so anytime you see them in a bond with another atom, it's a safe bet that the bond is polar. For example, HF contains a polar bond and is a polar molecule. Because there is no electronegativity difference between the two atoms in diatomic fluorine, F2 contains a nonpolar bond and is a nonpolar molecule. In molecules with more than one bond, we must consider the molecular geometry. For example, carbon dioxide contains two polar bonds. We can show the oxygen pulling electron density towards itself with these arrows, where the plus end shows where a partial positive charge resides, and the head of the arrow shows where the partial negative resides. These two arrows cancel each other out because of the linear molecular geometry. For this reason, carbon dioxide is a nonpolar molecule. Contrast this with a water molecule. H2O contains two polar bonds with electron density that adds together, piling up on the more electronegative oxygen atom in the bent molecular geometry, resulting in a polar molecule. Let's work through some more examples. In difluoromethane, we know that the 4 electron domains make the molecular geometry tetrahedral. The carbon-hydrogen bonds are relatively nonpolar, while the carbon-fluorine bonds are strongly polar. If we redraw this molecule to make it look more three-dimensional and add in the polarity vectors, we see that the bond dipoles will combine to form a molecular dipole. In ammonia, 4 electron domains give us a tetrahedral electronic geometry, but the presence of the lone pair of electrons give us a trigonal pyramidal molecular geometry. Each of the nitrogen-hydrogen bonds is strongly polar, so adding the polarity vectors, we see that ammonia will be a polar molecule. If we consider the sulfur hexafluoride molecule, we see that 6 bonding domains give us an octahedral molecular geometry. The sulfur-fluorine bonds are strongly polar, but the symmetrical shape of SF6 causes them to cancel out, giving a nonpolar molecule overall. Let's compare that result to bromine pentafluoride. This molecule also has 6 electron domains, giving it an octahedral electronic geometry. One of the electron domains is a lone pair of electrons, though, so BrF5 will have a square pyramidal molecular geometry. The bromine-fluorine bonds are polar, and adding up the vectors, we see that they do not cancel out, so bromine pentafluoride is a polar molecule overall. As always, I'll leave you with the parting thoughts of the authors.